All right, here we have a an unbalanced chemical equation. So the installment we'll be doing on this video is going to be balancing and mole ratio. Balancing and mole ratio. So with this, the chemical equation we have is V2O5 HCl plus HCl yields VOCl3 and H2O. So the first thing we need to do in balancing our chemical equations is creating a shopping list. And I will say one of the main things we need to recall from any of our previous courses is going to be the lesson on least common multiple that you see here at the bottom of your screen. And also that when we are balancing our equations, we want to leave hydrogen to be second to last that we balance, and oxygen to be the last element that we balance. And that's because these particular elements typically either are coupled together or they appear diatomically or in twos in nature. So as you see here, I've gone through and I've done my first step, which is creating my shopping list. I have written each particular element on my reactant and my product side. Along with that, I have placed how many of each element are there. And now I'm going to go back, and other than my hydrogens and oxygens, I'm going to look for the anomalies, which would be anything other than those two that need to be balanced. So it looks here that my first element and my last element are not hydrogen or oxygen, so I'll start with those. I have two V's on my reactant side and one on my product. So I'm going to first start with adjusting that particular compound or that particular element in my compound. So here I know in order to get the least common multiple, I will touch on that first for those that might not remember. Least common multiple is used to compare two or more numbers by which number will occur in each number line first. Okay, so the least number reached by counting by each number. So our first example here, and it may be difficult to read, but it's discussing the least common multiple of the numbers 2 and 5. So if I count by 2's and I count by 5's on a number line, which number will occur on both of those lines and be the least one? So I'm going to count by 2's. So I have 2, 4, 6, 8, 10. Then I count by 5's. And I want you to stop once you hear a number that you have already heard. So always start with that smallest number, count up a couple of spaces, and then go to your next one. And whichever number is the smallest on that line that is also on that first, you are at your least common multiple. Okay, so 2, 4, 6, 8, 10, counting by 2's, 5, 10. So it's going to ask you which number is smallest and in each line. So out of my 2's, I can get to 10. And out of 5, I can get to 10. So my least common multiple between 2 and 5 is 10. Okay? Once again, we're going to do this with the numbers 3 and 4. So we count by 3's, 3, 6, 9, 12, 15. And then count by 4's, give us 4, 8, 12, 16, and 20. And if we look, what number appears on both number lines? For those of you that picked the number 12, you are absolutely correct because I can count by 3's and get to 12, and I can also count by 4's and get to 12. So let's go back to our equation and give that a try now. So we know between the numbers 1 and 2, the least common multiple there is going to be 2. So we'll need to change that first compound here, or the first element, to 2. So we know in order to get a 2 from a 1, we would place the number 2 here. And whatever we have done, we need to adjust our shopping list. So we know instead of 1 vanadiums, we have 2. We must also recount our number of oxygens. So this 2 also gets distributed here, which is 2. But always be mindful to check your second compound because there's also an oxygen there. So we have a total of 3 oxygens now. And I know you said, Erica, you stated that we should leave those till last. If they are attached to a compound that we are working on, we must update that shopping list. Okay? And we also need to go ahead and adjust our chlorine. So we have 2 times our chlorine, so 2 times the Cl3 would now give us 6 chlorines. All right, so now we know our vanadiums are balanced. We know oxygen should be last for us to work on. Hydrogen is second to last. So let's look at our chlorines. I have 1 chlorine in the reactant and 6 in the product. How would I change that? The least common multiple between 1 and 6. I'm going to go on out and state that you all yelled at me from your homes and said, Erica, the least common multiple is 6. So we're going to go ahead and add that 6 there because there is no max on the number of moles that can be in a balanced equation. As long as they are the least common or the least number possible, then you are spot on. So let's go ahead and adjust our list. We said that we were adjusting the chlorine. So we know our chlorine is now 6, but our chlorine is attached to our hydrogen. So we must also adjust that portion of the list so that 6 is also distributed to that hydrogen. So let us see what we have left. We have 5 oxygen and 3 oxygen. We have 6 hydrogen and 2 hydrogen. So what would we want to do in order to adjust? Because we should be doing hydrogens second to last. So the least common multiple between 2 and 6. So if we count by 2s and count by 6, I'm going to reach 6 on both number lines. So what would I multiply by 2 to get 6? All right, I hear you yelling at me from your home. You said, Erica, it's going to be 3. So we're going to now update our list for hydrogen. So we have 3 times 2. That makes 6. But do not forget that oxygen. We need to adjust him. And this problem makes it very apparent why we leave oxygen last. Because adjusting our water molecule, we now have 3 oxygen in our first problem. And don't forget, there were 2 oxygen in our first portion of our product. So there's 2 and 3 because that 2 was distributed to each element in that first compound, and the 3 is distributed to each one in that second compound. So 2 oxygens and 3 oxygens will give us a total of 5. And there we have a balanced chemical equation. Now, you may be asked, What is the mole ratio? So in order to do mole ratio, you would need to have a balanced equation. So mole ratio. Step one, is your equation balanced? If it is, you are good to go. So balanced, yes, you can complete the ratio. If your answer is no, you must go back and balance your equation. But because we are already done with an equation, we're going to use this one as the problem for our ratio. And I want us to think of a mole ratio of the number or moles of a reactant over the moles of a product. Okay, reactant over product. So if a question were to ask you, what is the mole ratio of HCl to H2O? Okay, so you'll utilize that same balance equation from your previous problem, and now you're going to determine your mole ratio, remembering that we're going to have reactant over product. So if we look at hydrochloride or HCl, we're going to have 6 moles of HCl for every 3 moles of water in this problem. So remember, it is your reactant over your product. And you may also be asked a certain problem where it'll give you a number of moles and ask you to determine how many of something could be made. So say you are given how many moles of H2O will be produced if 15 moles of HCl react completely with V2O5. So pause the video, write down your problem, and come back and we will go ahead and set this up using dimensional analysis. All right, so let's take a look at the problem you just wrote down and determine what information is necessary and what information is a distraction. So we're looking at how many moles of H2O. So that's the main premise of our question. How many moles of H2O, okay, will be produced if 15 moles of HCl reacts completely with V2O5. So if you look back, did our previous portion of this, meaning our ratio question, did it even ask us anything about the V2O5? It didn't. Because it asks us for the ratio of this reactant and this product. So in this sense, I want us to look at the words react completely with B2O5 as distractors. Those are not necessary because the question is asking us for the moles of H2O. So that is what our DA problem is going to solve for. Here, we are going to use our mole ratio. So in this first slot, we're going to use our mole ratio. But we know whatever unit is on the left side when using DA, go right there. And in doing that, we'll know which number from our ratio needs to go on top and which one needs to go on bottom for the purposes of solving this question. And the good thing about dimensional analysis, as long as those terms stay coupled together, it does not matter which one is on top and which one is on bottom. So for this one here, we're going to say that we have 3 moles of water, or H2O, and it's going to be married to the 6 moles of HCl. All right. Whatever unit we have on the bottom will go on our next line. So mole of HCl. And if we go back to our problem, because we've already utilized the information from our ratio, we now need to go back and find the term or the number that goes with mole of HCl. And what do we have? Absolutely. We have that 15 moles there. It's not married to anything, so we place that over 1. And now we get to do the wonderful crossing out of like terms to make sure that we are left with the unit we need, which we are. We're left with mole of H2O. Multiplying out, 3 times 15 is going to give us 45. 6 times 1 is going to be 6. So now we are down to a simple division problem of 45 divided by 6. And it's going to tell us that we are going to be able to produce 7.5 moles of H2O. So if you look at a chemical equation in the sense of a recipe, it takes all of these items on the reactant side to create this particular product on the right side. Okay? So once again, I thank you for tuning in. I hope our balancing of equations and our work on mole ratio was helpful for you. If necessary, please pause, rewind, or even shoot a little comment underneath the video, and I will do my best to go back and address any of those questions you may have. So once again, happy studying, and I wish you the best of luck.